Welcome to Statistics for Clinicians. This will cover the major statistical techniques that are important for clinical research and also will serve as the review of statistics for the PRITE exam. Let's begin with prevalence. Prevalence is the number of cases identified in a period of time divided by the number in the population over that period of time. It's generally divided into current and 1 year and lifetime prevalence. Point prevalence is the number of people who have a case on a given day. That's usually best used if the disease has a clear biomarker. 1 month is more typically used in mental health. Have you been depressed in the last month, or did you meet criteria for MDD in the last month? 1 year prevalence will include people who have had the condition, but also will include people who've had the condition, that is, people who have recovered, and the same thing with lifetime. Then you're asking people, have they ever met criteria for MDD or whatever the disorder is under study. Here's an example of prevalence, national survey of 36,000 plus individuals. The 12-month and lifetime prevalence were 10% and 20% respectively. Again, this illustrates that the lifetime prevalence is going to be higher because it includes the recovered individuals. Incidence is the number of new cases in a given period of time over the number of people at risk during that time. Incidence and prevalence are related mathematically, as you can see in the formula there, but incidence data is much harder to find in mental health studies. People can rarely tell you exactly when their psychosis or their mania or their depression had an onset. Particularly, this is true in disorders like schizophrenia, where there may have been a long premorbid phase. So we tend to see much more prevalent studies in mental health. Now let's look at relative risk. Relative risk starts with a population. So here we have 100 smokers and 100 non-smokers that are followed for 5 years. And we then look at the incidence of lung cancer as we move along, because these are going to be new cases. And then we want to know what is the relative risk of lung cancer in smokers compared to non-smokers. Well, as you can see in the table there, people who smoked had a 20% incidence of lung cancer as opposed to 2% in the non-smoking group. So we plug those numbers into the formula as you see, and we get 0.2 or 0.02, which is 10. In other words, from this study, we conclude that smokers have 10 times the risk of lung cancer relative to non-smokers. Now, that needs to be distinguished from the odds ratio. Odds ratio begins with patients or cases. So here we would select 50 people with lung cancer and 50 people without lung cancer, and we would ask them about their smoking history. And now we can calculate the odds ratio. So here you see the rate of smoking is much higher in the people with lung cancer, and we plug those numbers into the formula, and we come up with an odds ratio of 21, meaning that if you have lung cancer, you are 20 more times more likely to have smoked. So what you obviously see here is relative risk and odds ratios don't necessarily give you the same answer because they're looking at the problem from a different perspective. Now, finally, a little more complicated one to understand is the hazard ratio. In the hazard ratio, the population is could be exposed to a treatment or a condition that should decrease the bad outcome, or conversely, you can look at whether they've been exposed to a hazard, such as a toxin or history of child abuse, and look if it worsens outcome. In the example I give you here, where we're looking at treatment, an HR of less than 1 means more survival, that is, a better outcome. So here we have people with a cancer who are randomized to either placebo or treatment, although I can't imagine where we'd be randomizing to placebo in a cancer study. But it could be any study where fatality is likely. And what we can see here at the two curves, the treatment group is surviving longer. There's more of them left. We can then calculate a hazard ratio, and I don't have the formula there, but really what I want you to do is just look at the concept. And here we have a hazard ratio of 0.38, which looks at the fact that it's less than 1 and statistically significant means that the treatment is improving the survival rate. And if we wait until the study completely ends and look at the total data, we can use the data at the end point to calculate the relative risk. A little point to remember if that question comes up on the exam. Now let's shift gears and talk about validity. This basically refers to whether our measurements reflect reality, and these are usually rating scales and clinical interviews. And there are subtypes of validity. The first is content validity. Do the items on the measure make sense? So if you look at the PHQ-9, the items all correspond to the DSM-5 criteria. I think we'd all, as psychiatrists, we'd all agree on it. You basically need a group of learned people to look at the items on the scale and say, yes, I think those are a good measure of depression. Now, criterion validity is how does the test compare to the current gold standard, and that's concurrent validity, or how does it do about predicting something, or predictive validity. So the gold standard might be senior psychiatrists who interview the patients and agree that these patients have major depressive disorder, and then they all fill out the PHQ-9 and they all have high scores. That gives us concurrent validity. Predictive validity, we've developed a scale like the MCAT that is supposed to identify those who are at risk for autism. So if we follow those babies and infants into childhood, early childhood, and people with high MCAT scores do develop autism, then we say the test has predictive validity. Now, construct validity is a little more complicated. This means, does the measure work in terms of the model of the disorder? So let's say Beck's cognitive behavior therapy, the theory or the model is that the negative cognitions are related to depression. Therefore, if I take a scale of these negative cognitions, that should be correlated with a measure of depression if Beck's theory works. That is construct validity. Now, validity needs to be distinguished from reliability. So in reliability, if something's not reliable, it can't be valid. If it's giving us a different answer every time, if you step on the scale and it tells you you're 110 pounds, and then 3 hours later you step on that scale and it says you're 130 pounds, well, that can't be right. It can't be valid. On the other hand, something can be just because it's reliable doesn't mean it's valid. It can be consistently wrong. So if you weigh yourself on a scale at the office and it says you're 130 pounds and your scale at home keeps saying that you're 120 pounds, well, your scale at home may be consistently wrong. So even though your scale at home is reliable, it's not valid. Now, in psychiatry and mental health research, we're very interested in retest of reliability. So if we give the PHQ-9 to somebody on Monday, and then we give it to them again on Tuesday, it should roughly give us the same score, because we generally don't expect depression to resolve that quickly, although that does happen, which is why developing scales in mental health is not easy. So we always have to assume that the variable or the disease of study is not changing during the interval that we've done the testing. And even more important in mental health is inter-rater reliability. Do two examiners come up with the same result? So In this situation, do two examiners come up with the same result? We usually use Cohen's kappa. So here two psychiatrists interview the same patient and provide their diagnoses independent of each other, and then we record whether it's present or absent for each rater. So as you can see in the table, rater 1 and 2 agreed that the disorder was present in 40 cases, and they agreed that it was absent in 40 cases, but there were 20 cases where they disagreed. So we calculate first the observed agreement, as you can see there, and we calculate what chance agreement would be, and that would just be 50%. And then we do our kappa score, 0.8 minus 0.5 over 1 minus the chance agreement, and we come up with a kappa of 0.6, which is not great. So if these two psychiatrists are enrolling people in a clinical trial, this is a problem because the people going into the trial will not necessarily have the diagnosis of interest. So what do you do here? Well, you decide which of these psychiatrists is the gold standard, and you train the other psychiatrists to do the interview the way the gold standard psychiatrist wants it done. Or you send them both to a third gold standard psychiatrist to get them both trained. And in clinical research, a fair amount of time is taken up by that process. All right. Now let's talk about a hoary old favorite, sensitivity and specificity. And this relates to how a test does against a gold standard. Again, it's a problem in psychiatry where we always don't have a lot of great gold standards. But let's say I'm a researcher and I developed a test, a video game, and this will diagnose ADHD. So here I get 95 kids, both those with ADHD and those with controls, and they take the computer test, and they're also assessed by the clinician, who is the gold standard. Again, we make a table here, and we see that the test and the clinician agree in 30 cases. They agree that the ADHD is absent in 15 cases, but then there are 50 cases where they disagree. So the sensitivity is calculated by cell A, the number of cases where the computer was right, agreed with the gold standard, over N1, the 60, the total of people who actually had the disorder, and we see that that is only 50%. And with specificity, we take the number of kids where the gold standard and the computer agreed that they did not have the diagnosis, and divide that by the total of number N2 who the gold standard said they didn't have it, and we see it's only 42%. So while this test is doing okay, it's certainly not good enough for clinical practice, where we'd want to get it up around 0.9. Otherwise, we will identify people who don't have ADHD as having the disorder and will miss true cases of ADHD. And in fact, this very thing plagues a lot of the commercially available tests for that purport to diagnose ADHD. Now, related to sensitivity and specificity is a concept of positive and negative predictive value. This is a little bit more precise. I'm not going to go into great detail about it. I would just know the difference and know that it has a different formula. And here we see our positive predictive value is 60%, meaning the computer test is better at detecting the diagnosis when it's there, versus negative predictive value is pretty weak at 42%. So you would worry more with this test that it's missing cases of true ADHD. All right, now let's talk about something very important. This is not just for the exam. This is really critical in reading the clinical trials literature. And we're going to talk about effect sizes. We're going to talk about variance, which is critical to understanding effect sizes as well as our traditional statistical tests. And we're going to talk about the number needed to treat, or NNT, or the number needed to harm, or NNH. All right. Let's start with some real basics, because I find people have forgotten a lot of this from their Statistics 101. So here's a set of data in the left column. I've taken the mean of that data, which is 49, and then I'm going to calculate the variance and the standard deviation. So at the top I have the variance, and you will formula for the variance, S squared, and you'll notice I take each data point and subtract it from the mean. Let's take the top row, that's 45 minus 49, negative 4, and we square it, and that's 16. And we do all of that, and that obviously removes the negative numbers. And so we then sum that. That's the sigma, and we get 9936. Now, by calculating the variance, we divide by n plus 1, and that's 621. And the standard deviation, in contrast, is the lower formula. We simply divide by n, but we take the square root, and that's 24. So obviously, what does this all mean? Well, flatly, the bell curve, the standard deviation, is going to tell you how spread out, or how much variance, or how variable the population is. And as I hope you remember from Statistics 101, the standard deviation defines the population that is within 68% of the mean, whereas two standard deviations is 2, is those data points that are within 95%. Now, we can use a standard score that tells us how many standard deviations above the mean we're working with. And the most famous of this is the IQ, where the mean is arbitrarily called 100 and the standard deviation is 15, such that 68% of the population is between 85 and 115. And we can have any kind of standard score. We have the SAT, the MCAT, they all have the particular number, but the principle is the same. Now, here are two populations. They have the same mean, but very different variance and standard deviations. Obviously, the skinny bell curve has low standard deviations. The scores all cluster around the mean, whereas the broad bell curve has high variance. The scores are all over the place. So let's think about the effect size conceptually. So let's say we have two populations, controls and diabetics, untreated diabetics, and we come in and we measure their fasting serum glucose. It will come as no surprise to you that the controls will have a glucose of around 90 to 100 and a very tight standard deviation, whereas the diabetics, untreated diabetics are probably going to have a much higher glucose, but also a fairly tight standard deviation. So this is, and if we conceptualize it, we take the mean of one group, subtract it from the mean of the other group, and divide by the standard deviation. Well, here the difference in the means is big, and the standard deviations are small, so that number is going to big, and that is big, and that's a large effect size. So when the effect size is large, the difference between two individuals in the different groups is almost always going to be bigger than the difference between two individuals within the group. All right, hang on to that thought. Now let's take a different situation. If we do a verbal test score, generally females will be identified as will have slightly higher mean on the verbal skills test. And you can see that there. However, there will be a tremendous overlap between the two groups. So here the difference in the means is small and the standard deviation is broad, so this is a small effect size. So when the effect size is small, the differences between two individuals in different groups is likely to be smaller than the difference between the individuals within the group. Just knowing that someone is a man or a woman or male or female is not going to be able to really tell you very accurately what their verbal test score is, because the difference between the individuals within the sex group is larger than the difference between the group overall. It's a small effect size. Now, I talked to you about it conceptually. Here are the actual formulas for calculating it. So if the samples are the same size, you just subtract the means and divide by the square root of the standard deviation. But you can still see that the bigger the standard deviation, the smaller the effect size. If the sample sizes of the groups are different, then you pool the standard deviations using the formula below, but you still subtract the means from each other. But again, the principle is the same. The bigger the standard deviation, the lower your effect size is going to be. So let's take some examples, clinical examples, to kind of make this more real. So let's say we have 20 children with ADHD and we randomize them to either a stimulant or placebo. So what you can see here in the stimulant group is that the ADHD rating scale scores really go down. Go from a mean of 31 to a mean of 18 with a tight standard deviation, whereas the placebo scores barely budge. They only go from 36 to 31, but again, a tight standard deviation. So let's stick that in our formula, and we get an effect size of 1.8. That's pretty big. Now let's take another example. Let's say we're going to take 20 kids with depression, and we use the Children's Depression Rating Scale to do this study. Again, we randomize them to placebo or antidepressant. You will notice that we do get a reduction in CDRS scores in the antidepressant group. We go from 60 to 39, but kind of a wide standard deviation in the post-treatment group. If we look at placebo, it goes down a little bit. We go down from 60 to 48 with, again, a wide standard deviation. So again, if we were actually to look at this graphically, we would see that the placebo group is improving a little bit, but the drug group is improving more. In fact, the slope of that line going down is greater in the blue group, the treatment group. So let's again do our calculation, plug in the numbers. We see that our effect size is only 0.57. And as we'll see, that's what we call a median effect size. All right, so there you are. There's comparing the effect size. And what does that all mean? Well, we have a convention called Cohen's convention, and this is important for you to memorize. It's going to be on the exam, but it's good for you to know when you're reading clinical trials literature. So a large effect size, 0.8 or above, generally means that it's easily observable at the level of an individual patient. So that's giving a stimulant to a person with ADHD, giving Xanax to a person who's acutely anxious, or injecting Ativan if a person's having a seizure, giving an antibiotic to a person with streptococcal pharyngitis. You're going to get the patient's going to say, I am better. Medium means you're probably going to see an effect of the group, but you're going to have to see a group of people. So let's take antidepressants. You start 10 people on an antidepressant, 6 people will come back saying they're better. But you never quite know, who got better on from a placebo effect, who got better from a drug effect. You're a little bit unclear. Generally, 0.2 and below, those are so small that they're not relevant at the level of clinical work when we're working with individual patients, but they may be very important from a public health significance. So the effect size of a carcinogen in the drinking water may be very small, just 0.1. But if that carcinogen, if millions of people are being exposed to that, you could raise the level of cancer in the population. Now, you'll never be able to tie that carcinogen back to any one person's cancer, but the general health of the population is decreased. So public health people are much more interested in, or don't ignore, small effect sizes. Now, you don't confuse statistical significance and effect size. Statistical significance is the probability that the finding could have emerged by chance. So p less than 0.05 is a less than 5% chance that it occurred by chance, and p less than 0.01 is a less than 1% chance that it's random. In contrast, effect size speaks to the size of the effect. The bigger the effect size, once the study is statistically significant, the more impact it's going to have at the level of the individual patient. And the bigger the effect size, the smaller the sample you do need to show statistical significance. So what do I mean by that? Well, if the effect size is large, you're going to see the results versus placebo much more quickly with a smaller sample size. So you go up here, we need a small sample size to get the effect at 0.05. We do need a few more to get the effect at 0.01. And similarly, when our effect size is small, we'll need a very large sample. So effect size has nothing to do with the truth of the matter. That's statistical significance. So when we have the small effect size, get a big sample, we show that it didn't occur by chance at the 0.01 level. It's just a small effect size. Now, from the effect size, we get an even more important variable, the number needed to treat or harm. So the number needed to treat is the number of patients that you need to treat to prevent one additional bad outcome. So if the drug has an NNT of 5, it means you have to treat 5 people to prevent one bad outcome. And the number needed to harm is the mirror image of that. If they're exposed to a risk factor, how many people do you have to expose to know that at least one has been harmed? So if a drug has an NNH of 50, it means you have to treat 50 people to produce that bad outcome. That is the side effect. So naturally, we want NNT to be small. If a drug's NNT is small and the NNH is high, that's sort of the ideal agent, because it produces its effect without producing harms. Its benefit to risk ratio is high. So let's go back to our NNT. To calculate NNT, let's go back to our ADHD study. Now we're going to use categorical data. Let's just say that anyone whose ADHD score went below 21 is a responder. And in the stimulant group, we have 7 of 10 are responders. In the placebo group, only 1 of 10. So we have a control event rate, which is 1 over 10, or 0.1. And then we have the experimental event rate, which is 7 over 10. And then we just subtract one from the other and take the absolute value. And then the NNT is the reciprocal of that. So 1 over 1 over 0.6, 1.667. So we generally round up or round down the NNT. So we get, from this ADHD study, the stimulant has an effect size of 2. Has an NNT of 2, meaning we only have to expose 2 people to the stimulant in order to say that at least one of them has responded. Now let's look at the NNT in our depression study. So let's say less than 45 is a responder. In our antidepressant group, 6 of 10 are responders, and in our placebo group, 4 of the 10 are responders. So we do the same calculation. 0.4 minus 0.6 is 0.2. Take the reciprocal, and our NNT is 5. So we have to expose 5 people to the antidepressant in order to say that at least one is a responder. Now, the PRIDE exam will often ask you to calculate NNT or NNH. So the formula you want to memorize is 1 over the drug treatment group rate of response minus the placebo rate of response. And then you've got it. Keep that formula in your head. Now here's a real life example. So I took a study from Wagner et al. And they randomized 364 people to placebo or sertraline. There's the graph. I looked at the responders and non-responders and plugged the numbers in. So actually from their study, they found an NNT of 10. They found an effect size, if we look down below there, that if you plug that into the formula I gave you earlier, then we get a Cohen's D of 4. And if you don't like doing the math on your calculator, you can go to that that website, and they will let you just plug in your numbers. It'll calculate your Cohen's D for you. So again, this confirms antidepressants have a medium effect size with a relatively high NNT. Okay, so now let's do our number needed to harm. So we record who had a side effect of appetite loss, and we can see that on stimulant, 20 of the 80 had appetite loss versus 10 out of 80 in the placebo group. So again, we just plug the numbers in the same way, and we get 0.125 minus 0.25, take the absolute value, 1 over 0.125 is 8. So our number needed to harm with appetite loss is 8, meaning we need to expose 8 people to stimulants to be sure that 1 got appetite loss. And because NNH is higher than NNT, that tells us, at least for this side effect, stimulants have a good benefit to risk ratio. Now let me shift gears and talk about some clinical trial concepts. All right, these are clinical trials, a study where you randomize people to treatment versus non-treatment, treatment versus placebo, and you're generally following them over time in order to see whether they respond or not. And we use 4 important concepts. This is critical for the PRIDE, but also important for reading clinical trials data. And I'm going to show you examples of each of these. The predictor is a variable that predicts outcome, but is completely independent of the treatment process. All right? It's nothing to do with treatment. A moderator is a variable that's present at baseline and it interacts with the treatment process, so it tends to be a predictor of outcome. So people with a particular moderator may respond better or worse than people without the moderator. Key point, moderator is present at baseline. In contrast, a mediator is a variable that is a part of the treatment process that influences outcome. All right? I'll explain that in a little more detail. Now, a confounder is a variable that's not part of the treatment process, but it nonetheless influenced outcome. We do not want this in our studies. This is usually due to a failure of randomization. The groups were just different at baseline, or they were treated on something other than something different was treated than the independent variable. All right, here's some concrete examples. So let's say predictor. Let's say we do a study of depression and CBT, and we randomize people to either tau or treatment as usual or CBT. You will notice that the people in the low SES group have more depressive symptoms at baseline, and they have more depressive symptoms post-treatment. Low SES here is a predictor of depression because if you're poor, you're more likely to be depressed, but it's got nothing to do with the treatment process itself. In both groups, CBT was better than treatment as usual, and if we did the calculations, the effect size is the same within each group, but the poor people were still more depressed at the end of the study. So here we would say that low SES is a predictor of outcome. Now that's to be distinguished from a moderator. Well, let's take an example. Doing CBT generally requires a lot of cognitive effort, doing homework and whatnot. So suppose we measure everybody's verbal IQ at entry into the study, and we divide our people into those that have an average or above verbal IQ and those that have a superior verbal IQ. And we notice when we're doing treatment as usual, let's say just supportive therapy, IQ doesn't matter. Everybody gets a tiny bit better, but there's no distinguishing based on IQ. In contrast, the CBT is not only better overall, but people with the superior IQ at baseline do much better, presumably because they resonate with this very cognitively complex treatment effect. So here we would say that verbal IQ is a moderator of outcome. Now, what is a mediator of outcome? A mediator is part of the treatment process. So the simplest mediator, if you do a study, people have to take their medication. So what we're going to do here in this study, we randomize to placebo or drug, and we look at whether that whether they have high or low levels of drug. Now, that doesn't matter for the placebo group, but let's look at the two solid lines. Green are people with low levels of the drug, and blue are with people with high levels of the drug or therapeutic levels, so obviously they do better. So compliance with medication is a mediator of outcome. And that's a very simple mediator. There are other more complex mediators. Again, the relationship of the therapist to the patient, how warm the patient feels the relationship is, those patients will do better. So patient-therapist relationship is a mediator of outcome. All right. Now I think we're ready to talk about our good old-fashioned statistical tests. If you understand effect size, it's much easier to understand the t-test. So the t-test, we're comparing two groups, and you can see the formula for effect size in the top, and notice how the formula for the t-statistic is very similar. So up top we have groups where there is a mean difference between the groups, but the variance is high. There's a lot of overlap between the groups. And down below, we see that the mean is, difference in the means is bigger and the standard deviation is tighter. So the t-statistic is going to be bigger in the lower group than it is in the upper figure. So what we do here, if we go ahead and calculate our t-statistic, we then look at our degrees of freedom, which is how big the sample size is. So that's n minus 2. So if our sample size was 10, then our sample size is 8, and we at the 0.05 level, look at the table there, you need a t-statistic of 2.3. On the other hand, if our sample size is 30, then we go down to 28, we only need a t of 2.0 to be statistically significant. And the bigger the t-statistic, then by definition, the bigger the effect size. So that's kind of the mirror image of what I said a little while ago. You can then get to the one-way analysis of variance, which is simply studying 3 or more groups. But the principle is the same. We're interested in the means of the 3 groups and the variance both among the groups and within the groups. And you calculate all those formulas, basically the smaller the within group variance, then and the bigger the mean difference between the three groups, then the bigger the F statistic is going to be. And you can walk yourself through the statistics. Maybe at some point we'll do that. For the sake of the Prite and for the sake of your general knowledge, just know that it's really just analogous to the t-test, where we're looking at ratios of the difference in the means to the variance within and between the groups. Now, often in clinical trials, we will do the two-way ANOVA with a repeated factor. So the first factor of the two ways refers to obviously two factors. And the first one here is obviously treatment, whether you're on drug or placebo. And the second factor here is time, with two levels here, pre and post. And that measure is repeated. And what we're interested in is whether the slope pre to post in the drug group goes down faster, or is significantly, the difference in the slopes is significantly different. And that tells us that the drug is making people better much faster than the placebo. So almost all studies contain a graph that looks something like this, and that's how you interpret it. Now, let me talk about some research statistics and research ethics. And this is increasingly on the Prite, but it has also been the source of a number of scandals in medicine right now. So let's say an experiment, we draw blood from 10 schizophrenics and from 10 controls, and we have the capacity to measure 10 proteins. And so we measure the levels of all these proteins, and we do a t-test comparing the levels of those proteins in all 10 of those groups. And you notice that for proteins 2 through 10, that no statistically significant difference, but for protein 1, the controls are higher than the schizophrenics, and that's significant at the 0.03 level. So I say, voila, I've discovered a protein that's very important in the pathophysiology of schizophrenia. Well, in reality, what I've done here is taken Excel and I've generated 10 columns of random numbers, all right? So how is it that that one test for protein 1 came out statistically significant? It's because when I'm doing 10 t-tests, the p-value is not 0.05, but it's 0.05 divided by 10. That's called the Bonferroni correction. So I should have only accepted that protein 1 finding as statistically significant if I got a p level of p005, and I did not. And of course, so if I did these 10 proteins, these could just be different random levels, and I have nothing at all. Now, what do unscrupulous or ignorant scientists do? They measure their 10 proteins, they do a t-test on each of them, they see that protein 1 is significant, and that's the one they publish. And that is referred to as p-hacking. And another offense is called harking, or hypothesizing after the results are known. So this scientist has found this protein, and he goes back and he says, oh, this is a protein that's critical in the cerebellum. He goes to the legislature and he constructs a whole theory around what protein 1 does and how it is involved in schizophrenia. And he gives you the impression in his article that he thought of that in advance and then tested that with just protein 1 and got a result. Now, science is often self-correcting because someone else is going to go out and measure protein 1 and they're going to find nothing, and quickly, 5, 6, 7 studies will be published refuting it. But nonetheless, p-hacking can do a great deal of damage. And that concludes this basic overview of statistics. I think you'll find this helpful for the Prite, but hopefully as you discuss research articles, and particularly clinical research articles in your seminars, hopefully this will illuminate this entire process. Thank you.